Hi there. In this video we're going to look at how we integrate curves that are given to us parametrically. So you'll recall parametric equations are where our x-coordinate is given as some function of our parameter t, and where our y-coordinate is given as some function of the same parameter t. Now I've sketched what our curve might look like here, and remember integration is where we want to find the area underneath the curve. So you recall that to find the area underneath this curve, we would really like to integrate y with respect to x. Now y here, if we're integrating with respect to x, really needs to be as a function of x. And if we've got two limits, the two limits denote what our x values go between. So we need x to go from a to b. Now one of the things students try to do when they see something like this is they try to make t the subject of their first equation, substitute it into their equation for y, and come up with the Cartesian equation, which they can then integrate. And the problem with that is often, if we make that substitution, it gives us something here that we just can't integrate algebraically. So we're going to look at a slightly different tactic, which makes this a little bit easier. The first thing we need to do is have a think about how we're going to manage this integral. So what we would really like to do, we would really like to find some way to not have to bother with rearranging this to get y as a function of x. We would really like to just integrate y as a function of t. Now here, to find the area, it needs to be with respect to x, which might cause a bit of a problem because it's quite hard to integrate a function of t with respect to x. However, there's a little trick we can do to fix this and to swap this for a dt. And it's the same trick we used when we looked at integration by substitution. And that is that dx is equal to dx dt dt. And that just falls out of the chain rule. So dx dt dt is equal to dx. So what we can do is we can make this substitution to find the integral of y with respect to t, dx dt dt. So y of t and then dx dt, that's going to give us a function which we're much more likely to be able to integrate than not having these substitutions, especially in an exam context. And that is definitely something we can integrate. Okay, so the next problem we have to solve is that in our original equation here, our limits were given to us in terms of x. Now once we integrate this as a function of t, it will be lots of effort to turn that back into some function of x to then substitute our limits in. What we'd really like to do is change these limits to values of t. So let's just have a look at x equals a. So if x is equal to a, well then we get a is equal to our function of t, and then to get t as the subject we need to do the inverse of x. So then we get t is equal to x inverse of a. So then our final equation is that the area is equal to the integral of y of t dx dt dt, and then our limits become t is equal to x inverse of a, and similarly t is equal to x inverse of b. And in a moment we'll have a look at exactly how to use this, but this is a really handy formula to have when we're looking at areas of parametric curves. Okay, so on to our example here. So we're given this curve parametrically, and we're asked to find the area bound between the curve, the x-axis, and the line x equals 1.5. And so it's this area here. Now in the last part of the video we derived this formula for the area of a curve in terms of things that we're given or we can quite easily find. So we're going to break this part into two parts. We're going to first of all actually find the integral that we need to evaluate, and then we're going to actually work the integral out. But taking this information and turning it into an integral is a whole step in itself. So let's work through that now. So the area is equal to the integral of y of t. Now y of t we don't need to do any work for, we're already given that. So that's 2t minus t squared. And then the next part is dx dt. So we need to differentiate this function up here. So we have x is equal to 1 over 2 minus t. Okay, and we're going to try and differentiate that. And now to differentiate something like this, we need to first write it as a power. So this is going to be equal to 2 minus t to the power of negative 1. Okay, and then this gives us something that we can fairly easily differentiate using the chain rule. So we're going to bring the power to the front, we're going to multiply by negative 1. We're going to differentiate the thing that's inside the bracket. So if we differentiate this, we get negative 1 again. And then we write the bracket down, and we're going to subtract 1 from the power. So that gives me negative 2. But then negative 1 times negative 1, they cancel out. So that just gives me 1 times by 2 minus t to the negative 2. So dx dt is this thing here, 2 minus t to the power of negative 2. Okay, and just for clarity, we'll put that in brackets. Dt. There we go. So the last thing we need to work out are the limits. Okay, so we need two limits. And the first limit, or the upper limit, is when x is equal to 1.5. So that's probably the most direct one that we can work out. So let's do that now. So if x is 1.5, we're going to use this first equation here to work out what t is. So if x is 1.5, we get 1.5 is equal to 1 over 2 take away t. Okay, now 1.5, it might make more sense to write that as a fraction. So 1.5 is 3 over 2. So let's make that change now. And then what we're going to do is we're going to multiply both sides by the denominator of this fraction, 2 minus t. So we get 2 minus t, 3 over 2 is equal to 1. If we divide by that fraction, we get 2 minus t is equal to 2/3. And then we'll add t to both sides and subtract the 2/3 all in the same step. So we get 2 minus 2/3, which is 4/3, is equal to t. So our upper limit, where this 1.5 is 4/3. Okay, so the next thing we're going to do is we need to work out this second limit here, okay, because we need a lower limit and we need to work out where that is. Now, this point is on the x-axis, which means it takes a particular value of y. Do you know what the value of y it's going to take? Exactly, that has a y coordinate of 0. So this time we're going to use equation 2. And we're going to let y equal 0. So we get 0 is equal to 2t take away t squared. And now this is a quadratic. It factorises, so that's how we're going to solve this. So we get t, 2 minus t. Now we're going to get two solutions from this. We're going to get t equals 0 from this first t at the front, and we're going to get t equals 2 over here. So t equals 0 and t equals 2. Now obviously we're only after one limit, so we need to work out which of these values of t correspond to this point. So what we're going to do is we're going to substitute these into our x values to see which of the x coordinates it makes sense for this to be. Now you might have spotted already that one of these solutions doesn't work when we substitute it in. Do you know which one? Exactly, it's this second one doesn't work, it's not valid, because if t is equal to 2, we get x is equal to 2, take away 2, 1 over that, which is 1 over 0, which again we can't have. So we'll get rid of that solution, and that just leaves us with t equals 0. Now if t does equal 0, x is equal to a half, which makes sense from our sketch. This one should be lower than 1.5, which a half is. So our lower limit is t equals 0. Okay, or to be consistent with how I've written it before, we'll just write 0 there. Okay, good. So now let's just do a little bit of tidying up on this integral, and then we can move on to actually trying to solve it. So we get a is equal to the integral between 0 and 4/3. Well, 2 minus t, you might notice that that's actually a factor of 2t minus t squared. So what I'm going to do is I'm going to pull a factor of t out of here. 2 minus t, 2 minus t to the minus 2. Okay, and then we're going to get some nice cancellation. So 2 minus t to the negative 2 times by 2 minus t to the power of 1. We add those powers, and that's going to give me 2 minus t to the power of negative 1. 2 minus t to the negative 1 dt. Or writing it slightly more nicely, we've got 2 minus t to the minus 1. That's 1 over 2 minus t. So we just get t over 2 minus t dt. So in a second we'll go on to actually work out this integral. If you want to give it a go, now's a good time to pause the video and see if you can. Okay, so we've just figured out that this is the integral that we need to evaluate to give us this area. So let's have a look at how we evaluate that now. So the first thing we might want to try is to see if this is one of our standard integrals, but in this case it isn't. The next thing we might want to try is to see if the top is the derivative of the bottom, and if it is we could write it as a ln, but in this case it isn't. But what we can do is we can manipulate this fraction and turn it into one where the top is the derivative of the bottom. So the first thing we need to do is this negative t. It would be really nice if that was positive, like the top t. So we're going to pull out a factor of negative 1, and then we can change the sign on the denominator of that fraction. Okay, so now what we're going to do is we're going to rewrite that fraction, and we're going to change the top of the fraction ever so slightly, but not in any way that's going to change the value of it. So we're going to have t over t minus 2, and what we're going to do is we're going to subtract 2 from the top, but then we're going to add it back on. So we've not changed the value of that fraction, we've merely rewritten it in a slightly different way. But what that allows us to do is it allows us to split our fraction into two parts. The first part, t minus 2 over t minus 2, and then the second part, plus 2 over t minus 2. Now, why is it useful to do that? Well, t minus 2 over t minus 2 just turns into 1, and then 2 over t minus 2. Now, the top is a multiple of the derivative of the bottom, so that is going to integrate to give me a ln. So let's carry on up here. So we now have, that gives me negative the integral of 1 plus 2 over t minus 2, and between 0 and 4/3. And what that's going to allow us to do is actually integrate this. So this turns into, well, the integral of 1 with respect to t is just t, and this is going to be some multiple of ln of t minus 2. Now, if we differentiate t minus 2, that just gives us 1, but we don't want 1 over t minus 2, we want 2 over t minus 2. So we need to multiply the whole thing by 2. 0 and 4/3. So now this negative at the front, we need to deal with that when we substitute these things in. Just need to remember our modular signs in the ln, because in this case we would have got a negative value here when we substitute the 4/3 in. Just need to be a little bit careful there. But let's do that first of all. So because we've got the negative here, what we can do is we can get rid of that negative and we can swap our limits around. Because then what that means we'll do is we'll just subtract them in the opposite direction. So let's substitute 0 in first. So we get 0 plus 2 ln of 0 take away 2. And then we're going to subtract 4/3 plus 2 ln 4/3 minus 2. Okay, now 0 take away 4/3 is just going to give me negative 4/3. Now ln of 0 minus 2 is just going to be ln of negative 2, but with the modular sign that turns it into positive 2. So this is going to give me plus 2 ln 2. And then similarly here, 4/3 take away 2 is going to give me negative 2/3, which when we take the modulus is positive 2/3, that's going to be minus 2 ln 2/3. Okay, and that's our answer. That is the area of this section of the curve.